Hi class, welcome to another session on digital principles and system design. So let us now discuss state assignment. Now before we discuss state assignment in detail, I would request you to go and study state reduction or state minimization first, because if you understand that, you'd be able to connect with this section even better. I mean everything, this will make more sense if you had understood state reduction first. So why do we have to do state assignment? Like we all know that the cost of a combinational circuit can be reduced by Boolean expression reduction techniques or K-maps, right? So state assignment procedure is used to assign binary values to states in such a way that the overall cost of the combinational logic circuit that drives the flip-flops are reduced. Now, it is necessary that no matter what binary value you assign to the state, the input-output relationship should not be jeopardized. The input-output relationship of the system should remain the same. Now, some circuitry take direct output from a flip-flop, from an external flip-flop with predetermined binary states. Now, this principle of assigning random state values does not apply if our circuit is one of these circuits. So only in circuits where, you know, irrespective where direct output from the flip-flop is not taken to drive the circuit, can we use this principle of random assignment of binary numbers to states be used. Alright, so let us consider an example where 010101 10100 is fed as an input to the circuitry whose state diagram is given below. Now, like I said, understanding state reduction would result in understanding this much better. So, just briefly, here A, B, C, D, E, F, and G are different states. So, state A remains unchanged if an input 0 is given and an output 0 is obtained. So if for every input that is 0, if the output is 0, then state A remains unchanged. If input is 1 and output is still 0, then A changes to B, and so on. So another example would be B changes to C if input 0 drives an output to be 0. And if input 1 is given and output 0 is obtained, then B changes to D. So this is how you would understand, this is how the state diagram works. Now, after applying the minimization principles, we'd realize that whether we have these 5 states A, B, C, D, and E, or whether we have those 7 states A, B, C, D, E, F, and G, well, whatever input-output relationship we had with those 7 states is same as the input-output relationship with these 5 states. So, instead of having 7 states, if I just use these 5 states, my circuit is still going to perform the same way. So, here, it is unaffected, like the input-output relationship is unaffected by the binary values that are assigned to the states. Therefore, we can proceed with the state assignment procedure here. So, I have states A, B, C, D, E, and A, B, C, D, and E, right? Assignment 1, assignment 2, and assignment 3 are 3 random state values that I've given to A, B, C, D, and E, right? So, assignment 1, these are just done randomly. I've not followed any sequence. There's no set rules to do this, right? You can do this randomly. Now, there are more than one, but these are not the only 3 possible combinations. You can have other combinations as well. However, it doesn't affect the performance, so I've just shown you these 3 examples. In case you have a circuitry where the performance is getting affected by the binary assignment, then this rule does not apply. Right, I'm trying to make this clear again and again. So if you consider the state assignment 1, which was the most straightforward binary values, like it's like the binary values are in sequence. So all the alphabets that were there in the state table, reduced state table, would be replaced by these binary values. Now, different binary values will result in different values in the state table. However, as long as the input-output relationship is not affected, it doesn't matter, right? If for a particular input, my circuit is given a particular output and that is consistent, then it doesn't matter at all, right? So, of the 7 states that we use, only 5 states are mandatorily required for my circuit to perform properly, right? So I have 2 states which I don't care. So this can be used to further reduce the Boolean expression. Sometimes this can result in minimum number of logic gates to represent my circuit. However, it's not mandatory that a reduced Boolean expression would result in a reduced number of logic gates. So that's not like a hard and fast rule. Sometimes the number of logic gates might remain the same, but the number of states might reduce, and the amount of time required for the circuit to produce the output might reduce, and that would reduce the cost as well. Right, so finally, my state table, let me go a few slides back. This one, it has been replaced with this one, where I have replaced A with 001, B with 010, C with 011, D with 100, and E with 101, right? So my output were, if x is 0, then A remains unchanged, so therefore 001. If x is 0 and input a state 010 is given, then my output becomes C, so it is 011, and so on. So I've just replaced the A to E with binary values from the state assignment, and my input output has remained the same. So this is all I have to talk about state assignment. I hope you had a fruitful session learning about this with me. I shall see you again in the next video. Till then, take care.